Hello and welcome to this presentation. My name is Jonathan Heiss and I'm working with the Information System Engineering Group at TU Berlin. The title of this talk is Put Your Money Where Your Mouth Is Towards Blockchain-Based Consent Violation Detection. I did this work together with my colleagues Max Ulbricht and Eberhardt. The underlying procedure of our work is consent-based access control, which is a special type of purpose-based access control that is user-centric and particularly allows service providers to manage personal data of service consumers in a GDPR-compliant way. Now, how does this work? Let's assume we have a service consumer and we call her Kim, and she uploads a personal image of her to her favorite social media network. At a later point of time, the same Kim now uses her favorite image editing application and wants to edit the image that she has uploaded to the service provider. Now she has to grant permission to the third-party application to access this image at the service provider. How does this work? On an access request, the application user Kim declares consent to the service provider. Implementing this consent declaration as an access control rule, the service provider issues an access token that the third-party application can then use to access the personal image and then legitimately provide the image editing functionality to application user Kim. Now let's assume the following. Everything is the same until step 6, where instead of the consented image, an image is returned for which no consent has been declared. And in this case, a consent violation occurs. Now let's understand what's the problem here with consent-based access control and consent violations. First of all, consent violations can inflict high penalties on the service providers. The GDPR defines penalties of up to 20 million euro or 4% of the annual revenue of the service provider. At the same time, service providers have only deficient technical support to guarantee GDPR compliance, and especially no technical support for detecting consent violations. Next, consent violation detection itself is non-trivial, especially in operational systems. So consent-based access control very quickly ends up in a high number of access control rules, which means a high complexity for the access control implementation. Further, you have the third-party application that is the only party that witnesses such consent violations at first, has no incentive to report such a data breach to the service provider because it's not legally actionable. The only party that is legally full responsible for providing GDPR-compliant access control is the service provider itself. Next, access control structures are usually centralized and non-transparent. And this means that service providers, they cannot review whether GDPR-compliant access control measures are implemented by the service providers, but instead they must fully rely on the service providers, and if a consent violation occurs, service providers are threatened to lose the trust of their service consumers. Now, how do we approach these problems? We approach these problems by introducing a system for economically motivated and public verifiable detection and reporting of consent violations. By using our system, service providers can advertise an economic commitment to GDPR compliance on the blockchain that serves as a monetary reward for application users and third-party applications to report consent violations. If we break this down in individual contributions, our first contribution is a consent violation detection technique that allows for public verifiability while preserving privacy of the service consumer, so protecting their personal data. Next, we introduce this consent violation technique into a system design for standard consent-based access control procedures, and this system design also allows to place incentives for violation detection. And third, we we provide technical support for fulfilling some of the service providers' legal obligations as defined by the GDPR. At first, we have to answer this question: how to make consent violations technically decidable? And therefore, we need two artifacts. On the one hand, we need the consent declaration, which specifies for each data item the consent. Then the proof of access, so an actual proof that a certain party has accessed a data item or not. And if we have both of these artifacts, we can determine whether a violation exists or not. A violation exists if data has been accessed for which no consent has been declared. And since this whole process should be public verifiable and privacy preserving, all artifacts should have the same properties. Now, consent declaration must be GDPR compliant, and therefore in our paper we provide a thorough legal analysis. In this talk I will just present the gist of it. And it says in Article 4 that consent must be a specific, informed and unambiguous indication of the data subject's wishes and given by a statement or clear affirmative action. Specificity and informed means that the data subject must be aware about who intends to process which personal data for what reason. The clear affirmative action says that the service consumer must proactively decide this consent declaration. So something like actively ticking a box or proactively choosing a technical setting. From our legal analysis, we derive our components for the consent declaration, that are the data to be processed, the identity of the data processor, the purpose for processing, and the binary consent declaration, which we model as a function that takes identity, purpose, and data as input and outputs a Boolean value. Now, going back to our initial example, let's see how the technical representation of each of these artifacts looks like. So the third-party application, for each data item that it requests, it must specify its identity and the purpose for processing, which is image editing. Receiving these three tuples, the application user declares consent by applying the consent declaration function on each of these tuples and thereby adds a Boolean element to it, true or false. On receiving the consent declaration, the service provider now constructs a consent policy that is public verifiable and privacy preserving. And a central role here plays the access token that is issued by the service provider. The access token implicitly represents the identity and the purpose of processing. So what the service provider does first, it replaces the identity and the purpose with a generated access token. And then, since we cannot reveal the access token to anyone else but the third-party application and the application user, the service provider generates a commitment to the access token, which is then appended to the consent policies. By using the access token, we can later see whether data that has been accessed with these access token belongs to a certain consent policy. Now let's see how a proof of access is generated. And here we see the third-party application receives a response from the service provider that contains the data that has been requested. And the technical representation here is a key value representation. So for each data, a value has been returned or not returned. And now, based on this response, the third-party application now constructs a proof of access, which is also public verifiable but privacy preserving. And therefore, we leverage zero-knowledge computation. Zero-knowledge computation allows a prover to convince a verifier that a certain computation has been correctly executed without revealing the computation itself nor a private input to this computation. And in our case, we execute three operations in this zero-knowledge computation that are: we calculate the hiding mapping, so we replace every value that has been returned with a true and every value that has not been returned with a false. Second, we confirm the signature of the service provider to prove authenticity. And third, we commit to the access token to prove legitimate data access. And then we can later, as we'll see in a minute, compare these commitments to the access token of the consent policy and the violation proof and the proof of access. Given both inputs, we can now construct a violation proof. And a violation proof is valid if the zero knowledge proof is valid, if the access token commitments match, if data has been returned for which no consent has been declared, so a violation exists. We can determine the violation simply by looking at the Boolean values of the consent declaration and the proof of access. If the consent declaration says false, so that no consent has been declared, but the zero knowledge proof of access says true, the data has been accessed, a violation can be determined. Given the technical representation of consent violation detection, we now want to integrate this mechanism into a system designed for consent-based access control. And we design our system around three objectives. At first, we want to guarantee public verifiability of consent violations, and we also want to guarantee trustworthy, censorship-resistant provisioning of a monetary reward that serves as an economic commitment to GDPR-compliant consent and data management. Therefore, we leverage public, smart contract-enabled, cryptocurrency-enabled blockchain technology, such as provided by the Ethereum blockchain. The second objective is to preserve the privacy of service consumers and hence protect personal identifiable information. How can we do this when we use a public blockchain? Therefore, we leverage Socrates, which is a language and toolbox for zero-knowledge verifiable off-chain computations. And Socrates allows for verifying off-chain computed zero-knowledge proofs on the blockchain. Our third objective is to provide good integration with existing setups for consent-based access control. And therefore, we design our system with OAuth 2.0 implicit grant in mind, which is a prominent protocol that is typically used to implement consent-based access control. Now let's dive into our system design. So we have the same parties as we have in our initial example, but now as a first step, the service provider deploys a smart contract to the blockchain and deposits an economic commitment to it. This economic commitment is paid out to the party that first submits a valid proof of access and thereby proves a consent violation. So the commitment contract also implements the logic to validate a proof of access against a registered consent policy, and then pay out the monetary reward. As the second step now, the third-party application sends an access request to the application user, who then declares consent to the service provider, and the service provider constructs the consent policy as we know it, and then submits the consent policy to the commitment contract. The service provider then issues the access token that is forwarded to the third-party application, and the third-party application accesses the personal data using this access token, and can then, if it detects a consent violation, construct a zero-knowledge proof of access and submit this access proof as a violation claim to the commitment contract. Since the application user is also in possession of the access token, it can also query the personal data from the service provider. And if it receives the personal data, it can also determine whether a consent violation exists or not and construct a proof of access, which it can also submit as a violation claim to the commitment contract. Now, receiving such a violation claim, the commitment contract validates the proof of access against the corresponding registered consent policy, And if the proof of access is valid, the commitment contract first notifies the service provider about this consent violation, and the service provider has now the opportunity to close this data breach. But since we use a public blockchain, the commitment contract could in addition send a notification to the supervisory authority informing it about these consent violations, and thereby the service provider fulfills its reporting obligation defined by the GDPR. Then the commitment contract pays out the monetary reward to the party that has submitted a valid proof of access. Now the economic commitment is gone, the monetary reward is paid out, but the service provider can easily reactivate this commitment contract by simply depositing another economic commitment to the commitment contract. Let's now discuss some open issues with our system design. So at first, determining and reporting consent violations to the public blockchain also discloses these violations as a target for possible attacks. So an attacker could monitor the commitment contract for submissions of consent violations, and if determined valid, it knows that the service provider is vulnerable and the attacker could start an attack. As a workaround for this, we propose the following. The detector could first submit a commitment to the proof of access that does not reveal the consent violations. And then after an adequate period of time, the detector submits the plain proof of access to actually claim its monetary reward. In the meantime, the service provider has the chance to close the data breach and thereby protect against a possible attack. The second thing we have to discuss is how to deal with consent updates and consent revocations. So since we have a public blockchain in place that has a append-only immutable data structure, the way to deal with consent updates and revocations is to override old policies with new policies. What's important here is that we have to invalidate the old access tokens each time we override it with an old policy with a new policy, and for each newly registered policy, of course, we have to issue a new access token. The third thing is how to actually integrate our system design into an existing system. And the first thing here is we have a quite straightforward data scheme that mainly is represented as a key value structure. And this data scheme lends itself to be adapted through a simple API overlay. So just overlaying this key value structure over the existing data structure is actually a straightforward approach. And also we have to consider that a service provider probably has already consent policies registered. How to now integrate our system? We propose here an incremental rollout. So for every newly registered consent policies, this policy is also registered as a commitment contract. And for all old consent policies, every update to these policies would trigger registration as a commitment contract. Now let me conclude by summarizing our contributions again. So we have introduced a violation detection mechanism that allows for censorship resistant and public verifiable detection of violations to registered consent policies, and thereby also protects the privacy of the service consumers. Then we have integrated this violation detection mechanism into a system design that allows for economic commitments to GDPR compliance and also allows for integration with standard consent-based access control procedures. Third, we have provided technical support for the service provider to fulfill some of its legal obligations specified by the GDPR. Let's now look into each of these obligations. So by using our system, the service provider establish an auditable archive of consent policies, and are therefore able to demonstrate that the data subject has consented to processing of his or her personal data as required by Article 7 of the GDPR. Service providers implement mechanisms to become aware of personal data breaches and are able to notify it to the supervisory authority as required by Article 33 of the GDPR. And finally, by using our system, service providers can prove the implementation of appropriate technical and organizational measures to ensure and to be able to demonstrate that processing is performed in accordance with the GDPR as required by Article 24. So by using our system, service providers gain quite a lot and can avoid these high penalties as defined by the GDPR. And at the same time, they can increase the trust of the service consumers into the system, because service consumers can now review if GDPR compliant access control is in place. And with this, my talk ends. Thank you very much for your attention. If you have any questions or remarks, please get in touch with me or my colleagues. This is our contact information. Thank you and goodbye.